to our original Vesper theory. You have to fill in these notes as well. Okay? We're going to talk about the Vesper theory, by the way, something I did not talk about, and I will now, are the different types of bonds you can have. Okay? And this is the description of each of these bonds and how they're formed actually is part of what you'll need to know for the AP. First of all, there are sigma bonds. Okay? You see that's the first one there? Sigma bonds are covalent bonds, and all the ones I'm going to talk about today are covalent bonds, formed by overlapping s orbitals. Now, if you remember what an s orbital looks like, an s orbital is spherically shaped, right? So if I overlap two spherical shaped orbitals, that will allow these guys to actually have free rotation about them. It's the strongest of the covalent bond, and it allows free rotation. Now, that's the strongest of the bonds. A single bond is not as strong as a double bond, which I'll explain how they're formed and so on. But of the types of bond formed, of the sharing of electrons, we're just drawing two dots being shared when we draw an electron dot notation. And then we replace that with a dash. Well, I mean, obviously that's not really what it looks like. All right? So these are sharing by overlapping orbitals, and you can see the picture I've got on the next page. I actually have that picture popped up right here for me. Okay? All right, so a sigma bond would be the sharing of two orbitals. It's head-to-head, so that would allow free rotation. I have also drawn on this picture p orbitals. P orbitals, remember what they look like? A p orbital was like a dumbbell shape. Remember that? And they overlap differently. See, they overlap above and below the plane of that. So what happens is you no longer have free rotation. That kind of a bond is called a pi bond. Pi bond forms by overlapping p or d orbitals. And they happen in such a way, well, first of all, they're not as strong as the sigma bonds. And they happen in such a way, as you saw in my little picture, you'll see it again, that you no longer get free rotation about the bonds. Let me show you how both of those things apply to what we've seen in the past after you copy that. And what I'll probably apply to it when we do it next year. Free rotation about single bonds, which, by the way, I get single bonds even from sp3 hybrids, and I'll talk about that in a little bit too, like in an organic compound like this guy. It's why we were able to talk about having, remember, staggered and eclipsed formations, the Newman projections. They were able to rotate. All these guys were able to rotate. But when I had a guy like this, with a double bond, I drew him, and I even showed you, well, you can't really rotate them. The reason I can't is because this doesn't, double bonds aren't just a head-to-head sigma bond, but rather a pi bond, which actually, as you saw from the picture a minute ago, forms above and below the plane there of the sigma bond, and therefore you get no more free rotation. Now, you can form double and triple bonds by doing that. They're formed by a combination of sigma and pi bonds, and I want to show you those combinations here. Because, again, this, believe it or not, is actually on the test. I never covered this in Chem Organic, but I really should. I mean, if I'm going to be teaching the AP, I have to kind of cover this now. And it will make sense, hopefully, when I go back and show you some of the electron configurations, where these all come from and why they look the way they do. All right? A double bond, I've just copied this down for right now, but the picture will hopefully make sense. This is a picture that's not actually in your paper. I actually just made it up kind of today. A double bond is going to be one sigma bond and one pi bond. And when you're talking about organic molecules in carbon, you're talking about an sp2 hybrid, and I'll explain why it would be an sp2 hybrid. You'd have one leftover p that it would be able to form a bond, that pi bond with it, as well as sigma bonds. Okay? For a triple bond, it would be an sp1 hybrid, would be two leftover p's. And for single bonds, you would have sp3 hybrids. Now again, it doesn't seem to make sense. I'll try to show you why it makes sense in a minute. because carbon's unique. Carbon's a weird guy. He has what's called hybridization. We did talk about that. We did talk about, I'm going to refresh your memory on that in a second. So single bonds in organic molecules are sp3 hybrids, and they all form tetrahedral angles, if you remember, 109.5. Okay, so let me explain where these double, triple, and single bonds, especially in organic molecules, come from. And I want to show you by going back to something that we actually saw a while ago. Don't copy any of this down. This is not in your paper. I think for next year what I will do is I will put this all together. You had something very similar to this in your notes on organic, though. Okay, so let's just refresh your memory. If you were to have drawn carbon a long time ago in Chem 1, you would have drawn it like that. 6 electrons. Everybody watch here. 1s2, 2s2, 2p2. You would have drawn it like that. That's not really what happens when carbon forms a bond, though. What happens is, it turns out it's not very stable for it to have one completely empty p sublevel, not even half filled, and then a filled s down here. So what happens is that electrons kind of promoted up there, and then they're all smashed together and hybridized to form what are called sp3 hybrids. Okay? So instead of having a filled S and then, a half-filled p orbital here, half-filled, nothing at all on that one, you get pretty much this situation where every one of those becomes what's called an sp3 hybrid. They all kind of hybridize. They're all equal. Okay, they're not really just a 2s that's half-filled and a 2p that's half-filled. Okay, they all get smashed together. If you look back at your notes, you would see that that's what happens. In other words, it kind of looks like this. Remember the S shape? The S shape looks like this. It's a sphere. The P shape was a dumbbell shape. Guess what? When you hybridize these 4 guys together, you get the sp3 hybrid. It looks kind of like that. And that's why you get also a tetrahedral angle. 4 things bound around a central atom will try to get as far apart as they can, the Vesper theory says, and therefore you're going to form a tetrahedron, which basically why you have the tetrahedral angles around any carbon molecule that has 4 things around it. Okay? So, what I wanted to show you here a second ago is these are all going to be single bonds. If I'm going to bond a hydrogen to here or here or here, they're just going to bond head to head, and there'll be free rotation, or another carbon even, in a single bond. But watch what happens if I have an sp2 hybrid or an sp1 hybrid. All right, here I'm going to hybridize the s and 2 of the p's. Okay? This is an sp2 hybrid. Well, that leaves 1 p alone, and he can form that bond above or below, like the one that you saw the p's actually forming, that pi bond. That does not allow, that pi bond that can form between somebody else would be a double bond. That's why we show it like that almost, but we also need it because we need the springs so it would actually do this. All right, so you no longer have free rotation about that one. So if I were to ask you what kind of a bond is between a single bond and a carbon atom like this one here, that's going to be an sp3 hybrid. But this guy's going to be an sp2 hybrid because notice he hybridized an S and 2 of the P's. 1 P was left over. I could also get a triple bond. If I only go in S and 1 P, I'd have 2 P's left over for that third bond. Right? The 2 other bonds plus the sigma bond that's forming there. Okay? And that's where you get sp2 hybrids. From this one, you get sp1 hybrid as well. Now, all that stuff, I will probably go into a lot more detail. We're only reviewing today for the AP exam. And I'll try to get that across better next year when I first teach this. But something else we need to review today, by the way. All right, and that's just the same picture you saw a minute ago. All right, I want you to add on to this the same. Actually, you know what? I'll do that at the end. Don't do this. Let's stick with the notes. We're going to come back to that chart, and I want you to add on to that chart, which is actually in your other packet. I don't want you to have to get it out now. Let's continue with the notes you've got right now with the geometry. And I'll do that little chart at the end. All right. So, another review of what's going on here. Okay? If I know how many things are bound around a central atom, I'm going to use the Vesper theory to predict its shape. You know, it's really easy for just one single bond and 2 atoms. What shape does one single bond with 2 atoms have to have? Linear. It's got to be linear. But if I've got more than one thing bound around it, I got a lot of choice. I got to have a lot of choices I'm responsible for teaching you guys. Now, I've gone over all of these. This is something we actually covered pretty well. But as I was doing this today, I was shocked by how little you guys remembered from this, from the Vesper Theory. So I'm glad I decided to do this, because it is something you will need to do, being able to predict these structures. Okay? What you need to do is determine how many bonds or electron pairs are around the central atom. And then you're going to figure out what the shape would be based on that. And keeping in mind that either electrons or other atoms want to get as far apart as possible. The valence shell electron pair repulsion theory, Vesper theory, says that. These electron pairs or atoms are going to want to get as far apart as possible. Oh, around the central atom. I just forgot to get that. Okay? If you get a symmetrical arrangement, do you remember what happens there? Like, for example, one of the symmetrical arrangements you're going to see, which is not on here, is carbon dioxide, which we did the other day, didn't we? We did carbon dioxide. We learned why carbon dioxide's most stable resonance structure looks like this. Can't go into that again. We won't have time. But we know why it has this. I'm going to finish this sentence in a second. But let me explain to you. If I've got polar bonds, and this guy right here, this oxygen right here, okay, he's pulling that way. And this oxygen right here, he's pulling this way. Okay? And you can see that they're all linear. Okay? What's going to happen? You're going to have, even though that's a polar bond here and that's a polar bond there, what's the molecule going to be? Nonpolar. Just like a tug of war. Remember doing that back in the beginning of this year? That was a big deal. That was a big concept to get across from you. If I have symmetrically arranged polar bonds, I'm going to get a nonpolar molecule from that. We did labs on that. We made models with it. We practiced it. We did a lot of stuff on that because it was one of the only difficult concepts in that first chapter. Okay? Let's practice that right now. And we'll kind of also review a little bit of our electron dot notation stuff, for Victor's sake, if not for yours as well. I taught you a new way to do these. The new, you already have this chart, right? Okay. I taught you a new way to do these, the needed, available, and shared. Okay? So let's talk about that. Let's do it. You'll notice that the ones I'm going to do here are going to be pretty darn easy. All right? But let's just go with it. CCl4, needed, oops, I need green here. Needed, available, and shared. Okay? I don't know how much room you've got there. All right? You're going to probably have to write pretty small. What I'm going to do is I'm going to use this whole space to do CCl4 and then erase it. And then I'll use a whole space to do H2O. I also need you to add a column in here, which I don't think is on your paper. It should be the shape. You have room for the shape there? Column? Right? Okay. All right. Needed, available, and shared. How many are needed? How many electrons are going to be needed? Well, you go by, the octet rule. And the octet rule is pretty cut and dry for most guys. Carbon, chlorine, they want 8. Okay? Who are exceptions? The big exceptions we have to know, hydrogen and borons, another big one too. Okay? So they want 8. I have how many total atoms that want 8 electrons? 4, and 1 is 5. 5 total atoms want 8 electrons. 8 times 5 is 40. How many are available? Well, I've got 4 chlorines. So 7, and there's 7 in the outer shell for him. So 7 times 4 is what? 28. And I've got 4 more for carbon. That's how many? 32. That leaves a total. The difference between that is going to be 8. I'll have to share 8 electrons. This is how you do difficult ones. Although you could have probably done this one on your own, this is how you do difficult ones. 8 means I have a total of how many bonds? Since they're sharing 2 apiece, I'll have 4 bonds. So you now draw your central atom and the skeletal structure. Here's my central carbon atom. I kind of want to put the I'm going to put the carbon here actually, and I'll put my chlorines around it. Okay, and I want to connect them with I want to connect them with bonds. Bonds represent shared electrons, and this is nice. It all works out great. Unlike the last time where I might have had something like, well, I need 5 bonds, but I only have 4. What would I have to do if that were the case? I'd have to make double bonds or triple bonds even sometimes, right? Well, this is an easy one, and so will these other ones be pretty easy. I'm not going for how to do needed available share today. I'm trying to teach you what happens to the shape. All right, let's finish these up. I still have, well, I have 32 available. I've only taken care of 8 with the bonds. So 8 from 32 is 24, right? Is that right? 24? So I need, you put them around the outside ones, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And sure enough, there's my structure for CCl4. Now, you could have drawn him the old-fashioned way, just kind of like a puzzle piece, and giving everybody an octet, and it wouldn't have cost you, it wouldn't have been a problem at all. But I just wanted to refresh your memory on a needed available share just this one time. I'm not going to do it for the other guys. I may do it for boron because he's an exception, though. All right, here comes the big question. How many things are bound around the central carbon atom here? 4. 4 things get as far apart when they are in what shape is this? Tetrahedral. So I'm going to write down the shape is tetrahedral. Okay? And if I were to look up the bond polarity, I don't have a chart with the electronegativities. I'm not going to give you that. I don't even know if they'll give you that on a test, but they'll probably tell you, and you should at least be able to tell that a carbon-chlorine bond, what would you predict, looking at the periodic table, how far apart they are? What do you think? Polar or nonpolar? Remember, if they're farther apart, they're going to be polar. If they're really close together, or if they're the exact same atom, they're going to be nonpolar. Right. So I would predict this is going to be a polar bond. It's not polar by much, but it is polar. Now, if I have symmetrically arranged polar bonds, pulling that way, actually, remember, pulling at perfectly equal 109.5 degree angles, what does my molecule end up being?
Nonpolar.
Nonpolar. So there's a great, perfect example, review of how to do this. Let's take a look at water. I'm going to shorten this up a lot now. I'm not going to take that much time to do all of these, okay? Water, when you do him, you're going to find that you have an O in the middle and an H here and an H here. You draw your lines, and that's what your final structure looks like when you go to draw needed, available, shared, and all that stuff. There's your Lewis structure. You might say to yourself, okay, well, this is easy. I've got 2 things bound around a central atom. 2 things get as far apart when they are in a straight line. You're wrong. The Vesper theory says these things count too, right? Those electron pairs, they're going to repel. They're negatively charged. So I actually have 4 things bound around the central atom, but 2 of them, no, it's not tetrahedral. 2 of them, right, 2 of them are not atoms. So what you end up with is bent. Remember doing this?
Yeah.
That's right. It's been a while, but that's what it is. So this guy is bent in shape. Now, once again, I got polar bonds. The OH bond is a polar bond. You know that. You certainly should know water's polar. If you don't know that after Chem 1 and Chem 2, you haven't been paying attention. We talked about that with solubility and a whole bunch of other reasons, with hydrogen bonding and everything. But if I've got polar bonds, are these symmetrically arranged polar bonds? They are not symmetrically arranged by any means. If this were the oxygen and these 2 are the hydrogens, this side's going to be more negative. This side's going to be more positive. So one of the reasons water has such crazy properties, as you all know. So this guy, now here's the question. Since they're not symmetrically arranged, what is the molecule? It's still polar then. You have to realize, guys, this only works if you have symmetrically arranged polar bonds, that you will get something opposite. Doesn't work if they're not. And you know what else doesn't work? It's not like, and this happened in the labs when we were doing this, a whole bunch of people would have down non-polar for the bond type. Guys, if you've got non-polar for your bond type, what does your molecule have to be? Non-polar, no matter what. Period. End of story, right? Because if I don't have anybody pulling in any direction in a molecule, in an atom, they can't have it in a molecule. In any bond, they can't have it in any molecule. All right, now I wanted to do boron just with a needed available share because you do find this guy's a little weird. Okay? Boron only needs 6. Chlorine needs 8 apiece. 8 times 3 is what? 24. That's 30. Okay, so you got 30 for your needed. How many available do I have?
How much is boron?
20. Boron has 5.
Oh, 3.
Yeah. Boron has 5. And chlorine has 7 apiece times 3 is what?
What?
3. It's
Isn't that
3.
three?
Oh, my fault. I was.
Five.
No. Let's, because we are taping this. I want to make sure I'm just looking. I just looked at. Thank you, Victor. Why I'm doing anything for you, I don't know. But anyway, the group number is. I accidentally just looked right at the atomic number. The group number tells you the number of outer shell electrons. It's 3. That's how many has available. Chlorine has 7. 7 times 3 is 21. 21 and 3 is 24. Okay. All right, 6. Now, look here. This makes total sense. 3 bonds is all I have. I have the shared are going to be 3. There are 6 electrons, shared 3. And so my guy's going to look like this. My boron's going to be in the center, and my chlorine, I don't care where you draw them, it really doesn't matter. Chlorine, chlorine, and chlorine. The point is, how many things are bound around the central atom? And I'm going to compare this guy. I probably should have drawn him smaller so I can compare him to the guy below. You'll find 2 different answers, even though they both seem to have 3 different things bound around them. This guy really does have 3, right? Does everybody agree there's 3 things? Boron's one of those exceptions. He doesn't need an octet. He's still happy, and here he is. That's my 3 things. 3 things get as far apart when they are called what? Trigonal planar or triangular planar, however you want to call it. All right, so B, Cl, Cl, and Cl. I'm going to leave them up here. For the shape, is going to be triangular or trigonal planar. Is trigonal planar or triangular planar a symmetrical shape? Does it look symmetrical to you? Does to me too. It should. Should look familiar to you even from physics class where Schrader would tie a weight hanging from the ceiling and you calculate the vectors and all that stuff. You remember doing that. This is a symmetrical shape. These are polar bonds pulling outward from that one. So even though I have polar bonds, I have a non-polar molecule. But watch what happens with the last one I'm going to do down here. Thank goodness it's the last one. Okay? The last one down here for NH3. Again, I'm not going to do the needed available share because it's a typical problem, and I screwed up the last one anyway. So here's what nitrogen's going to look like. It's going to look like this, or ammonia, I should say. NH, H, H, and he'll have 2 dots up there. If you do the rules, you follow them, that's what you get. But you have to keep in mind, when you ask yourself the question of how many things are bound around the central atom, the answer is not 3 like it was up here. The answer is 4. And one of them is electrons. So basically, without the top, a tetrahedron looks like this. We call that what? Triangular pyramidal, right? So this would be triangular pyramidal. And I don't know. Actually, N and H are pretty close together. I don't even know if that's polar or non-polar. But does it matter? If I tell you the bonds for NH3 are polar, what does the molecule have to be? Polar, because this is not symmetrical. What if I tell you the bonds for NH3 are non-polar? What does the molecule have to be? Non-polar. It has nothing to do with the shape of the molecule at that point. Okay? So you'd have to look up the electronegativity differences between N and H and C. I mean, it's probably polar, and if it is, it doesn't make any difference. If those are polar, you still have a polar molecule here because they are not symmetrical. Now, the one thing I told you that you need to get out now to finish this up, to expand the chart there, I want you to do that right now real quick.
Which one?
It's the packet that had the color stuff on it. Oh, by the way, one last thing I almost forgot. These are the ones you're very familiar with, right? Linear, bent, triangular planar, triangular pyramidal, and tetrahedral is here somewhere. Here he is. Do I think they're going to ask you these other ones? I hope not. All right? But the different shapes you could have if you had 5 things around it, these are other possible shapes. They are on there. You can look them over. I would hope they would stick with these very common shapes, all right, that you would see on the test. All right, let's go back to show you that chart. Here it is right here. That chart is on the next to last page of the one that starts off with colors, the memorization stuff. It's on the next to last page of that. You'd have to add 3 columns to it somewhere. I don't care if you add them afterwards or before or both. All right? But it's the bond order, single, double, triple. It's just a summary. A lot of that stuff in that packet for memorization stuff, A lot of that stuff is summary stuff. So the next to last page says bond, single, double, triple, order, sigma, sigma and pi, sigma and 2 pi. All right. Well, you're going to add on also which are the longest, the shortest, the weakest. You're looking at it right there on the page. You can't miss it. It's right on that page. But you have to expand it by adding the charts that's not there. Add the columns that aren't there. And there are 3 columns that aren't there, right? So this one, and this one. They don't have to all go afterwards. Some of them could go on the other side if you can fit them. For next year, again, I will probably fix that chart, so we'll have them on there to begin with. You guys are the guinea pigs, first year doing something. Obviously, these aren't filled in because they're in between, right? Longest, shortest, obviously double will be in between. And you guys can copy all that down.